I appreciate very much this opportunity, and I thank Professor Abilio and Professor Walter Canieri and all members of the organizing committee of this amazing event. Thank you very much. My work is probability as a linguistic model. My plan today is to show the difference in mathematical way of thinking and epistemic way of thinking. The way we think determines the way we're looking at models of possible results. Models of possible results determine our interpretation of data, and data determine our way of degrees of belief. And probability is only a set of models, theoretical, mathematical, used as a language, an idiom, mathematical, quantitative, to express our epistemic perspectives about science, samples, decisions, and about our degrees of belief. At the time of Pascal and Fermat, the first combinatory analysis presupposes equal chances for each phase, but at that time, dice were not perfect symmetrical like today, probably. And when we um, use a real world dice, um, it may have some differences in probabilities. And this epistemic perspective requires us to throw the dice to see the results. And uh, the binomial formula and the binomial distribution um, are based on these presuppositions. And later, the binomial distribution uh, was approximated to the Gaussian distribution for large samples. Um, the distribution is the distribution of all possible results. And this is called sample space. And in basic statistic books, they are this kind of drawing that are completely deterministic because dealing only with numbers, we know all possible results in the case of dice or lottery. Uh, but in the case of scientific experiments, we are dealing with real world and we don't know the real shape of the distribution in play. In traditional frequentist statistics, unknown population parameters such as mean or variance are not treated as guessed estimates. Instead, we use estimators and confidence intervals to infer the value. The most common used estimator is the maximal likelihood estimation method. And in Bayesian statistics, we treat parameters as results calculated with probability distributions that reflect our degree of belief, using a prior distribution and updating it with data. The idea of Bayesian statistics is uh, uh, when we repeat several times the experiments and increase the quality of our evidence, we are approaching to the real value. And based on the, uh, we call them bridging principles, we can unify the frequentist perspective and the Bayesian perspective. Um, in the real world science, first we have theories of distribution models, and the sample size is calculated and the sample is modeled based on this theory of distributions, depending on the kind of results we are searching for. And when we have results of the studies, we see, I have experience with this in meta analysis, several studies evaluating the same question have different results. This shows that um, there is a contingency in each sample, in each study. And when we have only one result in hand, only one study in hand, where we are, how can we know that our result is a good representation of the population? There is a residual uncertainty. Uh, we try to reduce this uncertainty by using good models, but these models are theoretical. And when we use the model, we are believing, inferring, or expecting, or assuming that the model is adequate for the data under study. The acceptance interval and the relevance interval are used to evaluate and interpret the sample, but these intervals are based on the distribution. So we use theoretical models to interpret real samples. Uh, Frequently, especially in biological variables, the Gaussian distribution is very good. You can see here that there is only a slight asymmetry, but I have experience with variables like money and time, and they don't have symmetrical distributions. Gilly said that we can't use objective statistics in social sciences because of this problem. But time is not only a social science. I don't agree with Gillies about that. And we have, for example, in the regression models, the lines are the models. The lines are produced by the models, and the points are the real data. And we need to check if our models are good. Goodness of fit tests are made to evaluate the observed data uh, in comparison to the expected under the model. And we have some fit statistic to evaluate this. These authors surprised me with these nonlinear associations and very, very asymmetrical data. And uh, uh, we must have in mind that uh, there is residual uncertainty that if really our models are good for the real data. Fisher wanted a method that would allow us to obtain a distribution from an unknown parameter without having to assume a prior distribution, thus avoiding the subjectivity of the Bayesian approach. But in the end, fiducial probability is perhaps best understood as a compromise between classical and Bayesian views of statistics. That's my project. Uh, Only one view of statistic, a set of models that are used in a Bayesian way or in a Fisherian way, depending on the situation. Uh, the likelihood is inside the base equation. And you can see here the two problems of the Bayes theorem, the Prior's problem and the old evidence problem. The old evidence problem is simple when we attribute the value of one to the evidence because we know the evidence. And so we put one in the formula and it lead us to a contradiction when P, the probability of the hypothesis under the evidence is equal to the probability of the hypothesis. So uh, this problem is solved when we do not attribute the number one as a value for the evidence. We need to put here the accuracy of the way we evaluated that evidence. We use this in medicine with tests, and there is no test in medicine with 100% confidence. So we don't have probability of the evidence equal one. If this number is less than one, the old evidence problem is solved. The Prior's problem uh, uh, comes from this question: from where comes the probability of the hypothesis? In scientific studies, we use previous studies to offer the pretest probability. And uh, not always we have previous studies for the question. So we propose a hierarchy of evidence to solve this problem. And here, the another kind of formula for the Bayes theorem. Our proposal is in statistics there are Fisherians and Bayesians. In philosophy, there are objectivists and subjectivists. Fisherian and objectivists say, like the Tarski scheme, uh, but they say this using the model based on infinite. The problem of the Tarski scheme is from how can we evaluate the real world? That's the problem, and the Fisherians have the same problem. And here you can see what Bayesian says. Bayesian says that the prior probabilities are evaluated by current of bets and by Dutch book argument. Our proposal is unifying the two perspectives, and in the Fisherian case, B is the accuracy of the model, and in the Bayesian case, B is the best available evidence, hierarchically organized. Uh, there is an inherent subjectivity in priors. This is why Bayesians are called subjectivists. This is why Fisher tried to avoid Bayesian statistics. But the bridging principles allow us to unify the theories and reduce subjectivity. Our proposal is to create a hierarchy of objectivity of priors. We have already published this in a paper about medical reasoning, and uh, the hierarchy is that if you have a perfect evidence like this one, 7, that is accurate and checked by different investigators, so you have the maximal objectivity to estimate the priors. But sometimes we have evidence with less quality or specialist arguments, and we propose here a hierarchy of priors. And we believe that our proposal solves the prior problem in Bayesian thinking and in science in a unified theoretical linguistic model by using the best reference class available at the moment and the best model or the best evidence and taking a decision when it is necessary with the evidence you have or postponing it when possible. Taking a decision is not finding the truth. Taking a decision is deciding under uncertainty. Our proposal does not solve the old evidence problem, but this problem is related to epistemic perspective that creates a language problem. In medicine, there is no evidence with 100% accuracy. And I believe that is the case for almost all kinds of evidence in science. To state an evidence, it is necessary to evaluate the accuracy of the quality of this evidence, measured as a value less than one. In the book, The Intelligence Trap, the author shows a case in which the digital finger is wrong. So it's not 100% accuracy. What defines probability as a theory? We argue that probability is a theoretical linguistic model because it relies on idealized abstractions, mathematical language, in perfect dice and possible result distributions, and we make a unification of objective and subjective perspective. We need to believe that the theoretical distribution of expected possible results when infinite sample size is adequate or is fit to the reality of the population to build the objective perspective. By using bridging principles, we can unify the theories and uh, apply it to reasoning or to science. But what defines probability? It's not its applications. We use the model, the theoretical linguistic model, to make these applications. But what probability is a theoretical linguistic model? Thank you very much for your attention. We invite you for this beautiful place in December, running around the lake. Thank you very much.